All right, this video is for my Chemistry 120 class. The topic today is energy. We know that chemistry is the study of matter and energy. And so the topics in Chapter 4 focus on energy. So the unit for energy that we generally start with is calorie. Notice this is a lowercase c. And a calorie, the definition of a calorie is the amount of heat required to raise 1 gram of water 1 degree Celsius. All right. Now, I think this sometimes gets confused with the capital C calorie. Like, let's say you had a bowl of cereal this morning, and that bowl of cereal was 120 calories. Now, this is a capital C, not a lowercase c. A capital C calorie is 1,000 calories. And so most of the food that we eat is on the order of thousands of small calories, as they call them in the dietitian schools. So what you want to remember here is that 1 capital C calorie is actually equal to 1,000 calories, lowercase c. Or another way this is written is 1 capital C calorie is equal to 1 kilocalorie. All right. Now, let's say I want to convert this 120 capital C calories from my serving of cereal this morning. I want to convert that into smaller case calories. So what I would say here is 1 capital C calorie is equal to 1,000 lowercase calories, lowercase c calories. All right. So what I would get for an answer here, the capital C calories would cancel out, and I would have for an answer that my cereal this morning had 120,000 lowercase calories in there. All right, or small calories. Now, the unit for heat and energy in the metric system is the joule. So we need to have a relationship between calorie and joule. So here's the relationship. 1 small calorie, we'll call them small calories, is equal to 4.184 joules. I'm not writing very well today. All right, or another way we can write this is 1 kilocalorie, which is 1,000 calories, is equal to 1 kilojoule. And that's probably going to be more useful because, again, when we're talking, not 1 kilojoule, 4.184 kilojoules. 4.184 kilojoules. That's probably going to be the more important conversion because, again, most of the things we do on the human scale are in kilocalories and kilojoules. So somebody said, well, how many kilojoules was in your food, in this serving of your cereal this morning? What I would do here is I would say that 1 small case calorie is equal to 4.184 joules. And then if they want it in kilojoules, then all I have to say is that 1,000 joules equals 1 kilojoule. So there's my conversion factor. So the small calories are going to cancel out here. That's going to give me joules, and the joules are going to cancel out here, and that's going to give me kilojoules. So if I do this on the calculator, I would get something like 502.8 kilojoules. All right. And then if we're doing significant figures, I'd probably say, well, the 1 and the 2 were significant, the 0 wasn't. So to 2 significant figures, this becomes 5.0 times 10 to the second kilojoules. So that would be my answer, 5.0. Or that's probably the best way to write it. I mean, you could say 500 kilojoules, but this looks like there's only one significant figure, so I don't think you'd want to do that. I think you would want to write it that way, 5.0 times 10 to the second kilojoules. All right, so what are we going to use this for? How's it going to work? Well, one of the things we're going to do is, in your book, they talk about the efficiency of a power plant, the net efficiency. So this is the first equation that you want to focus on, and you may have some problems that are related to this. So net efficiency, and this equation is on page 159 in the Chemistry and Society 7th edition book. So page 159, they have an equation, they call it 4.2, and that's called net efficiency. And that's equal to the electrical energy produced. In this case, we're talking about electrical. I guess you could use this for other types of energy, but what we're going to focus on in this chapter is that efficiency of energy transformation. So we got electrical energy, and then we want to know how much heat. And I want to use the delta symbol to represent heat from the fuel that we're burning. So if we're in Kentucky, we generally generate our electricity through coal, and so that would be our fuel. How much heat do we get from the coal? That's going to be converted into electrical energy, and how much of electrical energy produced divided by the amount of heat from the fuel times 100% gives us the percent efficiency. So this is really important. In fact, a lot of people say this is where we will save the most energy. Instead of trying to make things use more and more energy, what if we made our machines, our cars, if we made those things a lot more efficient? We wouldn't have to use as much electricity. And just to give you an example, so let's talk about the efficiency of let's say a coal-fired generator plant. So most of the electricity that we have in Kentucky comes from coal-fired plants, and some of them are being converted over to natural gas. So let's say the coal-fired generator plant is only 37% efficient. And let's say that the energy required to heat your house is 3.5 times 10 to the 7th kilojoules. That's a reasonable number. All right. So how much coal do we have to burn? How much coal do we have to burn to get enough heat to generate this amount of electricity to get to our house? 3.5 times 10 to the 7th. All right. So what we know is we want to find out how much energy has to be generated by the plant, coal plant, or we'll just say by the plant. And we know that it only has a 37% efficiency. So what does 37% mean? It means 37 divided by 100. All right. And if we multiply that, we should get how much energy we need for the house. So the house, we said it needs 3.5 times 10 to the 7th kilojoules. So what we don't know is how much energy do we have to generate at the plant so that when it gets to your house, it delivers the required amount of energy of 3.5 times 10 to the 7th kilojoules. Knowing that the plant to your house only has an efficiency of 37%, or 37 over 100. So this is an algebra problem. We're going to solve for energy by the plant. That's our x. So we could make this easy. We just say x times 0.37. That's what 37 divided by 100 is, equals 3.5 times 10 to the 7th kilojoules. Yeah, my kilojoules don't look too hot there. 3.5 10 to the 7th kilojoules. All right, so what do we got? We're going to solve for x, so we'd have x equals 3.5 times 10 to the 7th kilojoules divided by 0.37. All right, so let's see what that answer gives us. All right, so when we do that, we get 9.5 times 10 to the 7th kilojoules. So 9.5 times 10 to the 7th. Yeah, let's do a better job with that. 9.5 times 10 to the 7th kilojoules. So that's how much energy it has to be generated by the coal-fired generator plant to get 3.5 times 10 to the 7th kilojoules of energy to your house. So this gap between what your house requires and what the plant has to generate, because it's only 37% efficient, those are big numbers. And so that's going to be a focus in the future, and it is today, but here's a place where you can earn a living if you can come up with a better way for plants to be a lot more efficient in the transmission of energy from the plant to your house. I mean, look where you could affect efficiency. You could make the plant itself more efficient. You could make the transmission of that energy more efficient from the coal plant to your house. They talk about a lot of that energy is lost as heat as it travels through the system. Or you can make the house more efficient, where it doesn't require 3.5 times 10 to the 7th kilojoules of energy to keep your house warm. So this is the kind of stuff that's interesting, and there's plenty to do in these areas. And if you like this type of thing, then thermodynamics is definitely one of the areas of focus for you. All right. So what we want to know then is how much energy can we get from maybe a piece of coal, or from, let's try something even simpler like ethanol or sugar. I mean, I think it's funny that people don't realize that when we start talking about energy, okay, so we maybe think of gasoline, maybe you think of natural gas. These are all hydrocarbons. These are all carbon, hydrogen based compounds. And so even the sugar that you ingest is a hydrocarbon. So that's what we don't need a chunk of coal and expect to get energy out of it. We eat sugar. So what we want to look at is a thermodynamic equation. All right. So what does a thermodynamic equation look like? Well, it looks like this. If I burn, so let's say we go to a natural gas plant. This is a little more efficient than coal. So we got natural gas, which is mostly methane, and we're going to react that with 2 moles of oxygen, and that's going to form as a product carbon dioxide, which is a global warming gas, and water. And a lot of people don't realize water also absorbs infrared radiation. It does contribute to global warming as well, the water in the atmosphere. All right, so here's our equation. First thing we need to know is it balanced. So we have 1 carbon on the reactant side, 1 carbon on the product side. We have 4 hydrogen on the reactant side. Oh, we only have 2 hydrogen on the product side. So we need to put a coefficient of 2 in front of the water. So that's 2 times 2. That gives me 4 hydrogen. And then I've got a total of 4 oxygen. I've got 2 oxygen plus 2 times 1, 2 oxygen. So this equation's balanced. And what's interesting about this, you will also see in this equation sometimes Out here, 802.3 kilojoules. All right, so what does that mean? That's the amount of energy released when methane burns in pure oxygen. So that's called an exothermic reaction. So if we draw a figure of this, this is what it would look like. It would be energy on the y-axis and reaction progress or time. Sometimes it can be written that way on the x-axis. So up here we start off with our two reactants, methane and oxygen. And because it's exothermic, that tells me that the products, the carbon dioxide and the water, will be lower in energy